So we have basic concepts. What are the tools we use for crypto or for security? One of the tools we use for security is cryptography. Okay. So this is just kind of an overview of what it is. What is cryptography, though? Anyone? A quick, easy definition. What is cryptography?
Encrypting stuff.
It's encrypting something. That's kind of using the definition in the definition.
You can lock data that only the person who has the key can look at.
Using key to lock, is that what you said?
Yeah.
Lock data, so, okay.
So it's like disguising information.
Disguising information. Yeah, cryptography means secret writing, but it's a way of disguising information so only certain people can decipher it, to read it, to understand it. So where do we need encryption? Yeah.
Sensitive data.
To protect sensitive data. What, like, give an example.
Like credit card information.
Credit card information. Where else? Sorry, he's moving his chair and I couldn't hear you. Text messages. Okay, so communication, if I'm communicating with somebody and I don't want other people to read it, maybe I should use encryption. Do any of you use encryption? Yeah. No? I see some no's, yeses. Actually, how many people think they never use encryption? How many people think they always use encryption? How many people think they sometimes use it? So if you ever go to buy something on the internet, if it's an HTTPS website, it's using encryption. If it shows a little lock icon up there, it's using encryption. Almost always, there's stuff on your phone that's using encryption to protect your data. Dual Mobile, for your login to the university, uses encryption. Okay, so there's a lot of different encryption out there. We try to keep it away from you having to manage, but some of it you have to manage. Okay, so some definitions, and there's a bunch here. Cryptography, the discipline that embodies principles, means, methods, and transformation of data in order to hide their semantic content, prevent unauthorized use, prevent undetected modification. So the art of protecting the data from disclosure and from modification, protecting confidentiality and integrity of the data. A cryptographic system is an information system that provides cryptography. That's the best way to put it. These definitions are actually from the National Institute of Standard Technology. So associated information assurance items interacting provide a single means of encryption or decryption. Single means when we say cryptographic system. There are multiple ways of doing encryption and decryption. We'll talk about many of those. Okay. I will use the term plain text to talk about the unencrypted data. That's your messages, that's your credit card number, that's whatever you want to protect. It's the input to your cipher, your encryption system, or the output from the inverse cipher, the decryption system. Ciphertext, that's the encrypted data. You give your plain text to the cipher system, the encryption system, it outputs ciphertext. Ciphertext, I don't have to protect as much. I can show you the ciphertext, and if it's a good crypto system, you don't know what it means. So there's no loss of confidentiality. And then I give it to somebody else who knows how to decipher it correctly. They can read it, they get the actual correct information. A good cipher or encryption system will prevent you from creating random ciphertext and sending it to somebody and then deciphering and saying, yeah, that's a reasonable message. Or, taking a plain text message saying, the exam is canceled, and ciphering it and sending it off and making people think it came from me. So the cipher is any cryptographic system in which arbitrary symbols or groups of symbols representing units of plain text. So it could be a single symbol, it could be a collection of them. A single letter, a group of letters, whatever. So that's what we mean by units. Or which units of plain text are rearranged or both. Okay, yeah, and we'll describe what that means, yes.
The cipher is used to change plain text to the cipher.
Cipher changes plain text to ciphertext. It's your encryption system. And it does that using where they talk about arbitrary symbols or groups of symbols represent units of plain text. That is the this part here. That's what we call substitution. I'm replacing the plain text with something else. Or just rearranging things, shuffling it, and that's called a transposition cipher. Or both, which is a hybrid cipher. Any good cipher does both. Any strong cipher does both. This is not, it does this to me. So we're going to use a lot of different notation here. That didn't work. Oh, this is a not true PowerPoint, so I can't do that. The original form of a message known as plain text, we're going to use the letter P to represent that, or M, sometimes for a message. C will almost always be used to denote the ciphertext. So the C there. E of P means I'm going to encrypt the plain text. So it's a function. I encrypt the plain text, I get the ciphertext. D is my decipherment function. So take the ciphertext, decipher it, get the plain text back. Often, because there may be confusion, we will use specific keys. A key is the secret value, like the password, that the cipher runs on. So we have one encryption algorithm, but different keys. The key is what keeps it secret. If you know the key, you can decipher the message and the algorithm. Okay. Some algorithms use multiple keys. And so because of that, was there a question? Or was that behind you guys? Huh?
Sounded like it was coming from the computer.
Yeah, it sounded like it was coming from the computer too.
Also, John Schiff, he wanted to look.
You guys hear where that's coming from? Is that from you and that Coeur d'Alene talking? No? Zach, was that you? No, so it is somebody else. Okay. Yeah. If you have to log in online, like you're out because of an illness or you're Coeur d'Alene, do try to pop up chat if the audio doesn't work. Okay. All right. I'll include the keys as a subscript, or I'll just put it as like the first parameter of the function. Encrypt, this is encrypt plain text P with key K. Sometimes it's just hard to write the subscript. Okay. Encryption of an encrypted plain text should return the original plain text. So we encrypt and then we decrypt it. We should get back the original. That's the goal. Oops. Everybody got that? That's just our mathematical notation here. Okay. Encryption key. I mentioned the key. A cryptographic encryption key is the secret value used to provide a unique encryption function for the message. So we have our plain text. We encryption using the key to tell it exactly how to encrypt it. We get our ciphertext. We use the key to tell it how to decipher it. We get this plain text. Now, there's a lot of subtleties to this we'll go into depending on the algorithm. I say the key is optional. There are some encryption systems, old ones like the Caesar cipher, which I'll talk about. There was no key. Okay. Or the key was the same for everybody, so there was no key. Hey, but it worked. You know, you shave the slave's head, you tattoo the message on their head, you wait till their hair grows back, you send them off, but it's encrypted just in case somebody captures the slave and shaves their head. You know, hey, Julius Caesar was creative. It was a slow form of communication, by the way. Okay, cryptographic classifications. Sometimes we use a single key, sometimes we use multiple keys. When we use a single key, anybody who has that key can encipher and decipher. So it has to be what we call a secret key crypto system. It's also called a symmetric key crypto system. Symmetric because you and I both have the same key when we're communicating. Asymmetric, we use what's called public key, and I'll go into details on that later. There's two keys. There's a public key and a private key. They're related. I can take my private key and encrypt a message and send, well, no, let me rephrase that. You can take my public key, encrypt a message, send it to me. I'm the only person in the world who can decrypt it using that private key. So it's a public key. Everybody in this classroom can see it. Everyone can use it to send me a private message. And everyone in this room can look at other messages sent by other people and not be able to read them. Where a secret key, I use a secret key and you use the same secret key to encrypt the message. Everybody in the room who knows that secret key can also read it. So it's a pretty cool system. We'll explain it later. How is the plain text process? One bit at a time, one character at a time. That's called a streaming cipher. Chunks at a time, blocks at a time. It's called a block cipher. How do we do it? Do we just rearrange the letters? That's transposition, or the bits. Replace them, that's substitution. Hybrid is both. And we classify crypto systems based on these different terms. Okay, so what do I mean by block cipher? Like I said, it takes one block of information at a time using cryptographic key. So the DES algorithm, the data encryption standard developed in the late 70s, did 8 characters at a time, 8 letters. Or 8 letters, they can be represented using 8 bits each in ASCII, so it's 64 bits. So it took a 64-bit block of text and encrypted that at a time. Modern algorithms, they can still do 64, they can do 128, they can do 256. So a block cipher algorithm, the length of the input block is the same as the length of the output block. Okay. Now, ask you a question. So I'm using a block cipher. Why? Because, hey, now they got 64 bits they have to decrypt and not just 8 bits for a single letter. It's harder work for them, right? I'm logging into a system remotely. I type in my user ID, GMAF, I hit return. That's 5, 6 characters. But it's a block cipher that encrypts 8 characters at a time. Does it wait till I type the next 2 characters before it sends it? Because I only had 6, the input. Block cipher needs 8. So either it pads it, adds extra. Well, what's it always add? I want it to be something different than what I typed. Is it, but detectable, is it always zeros? Then the thing's not as strong. Where stream cipher would encipher, oh, you sent 6 characters, I'll just encipher those 6 as they go and be done with it. And so we have to worry about that either way. Whenever I'm using a block cipher on a file, that last block in the file may have some padding in it. And we have to be careful because that can help the cryptanalyst, the attacker. Okay. And so that's just something to think about when we look at these. There are ways around it. We'll get to those. Stream cipher. Like I said, each bit or byte of the data stream is encrypted separately. A stream cipher processes the input elements, continuously producing output one element at a time. This works really well. You think about something like a streaming video, if it's encrypted, you know, or you're texting or emailing or just typing characters in. You know, it enciphers them as they go along. But you want strength. You want to be able to confuse the attacker as much as possible. You want to be able to mix those things up between the different letters. Again, there's ways to do it. We'll talk about that. Okay. So block, I thought the terms were here, they're not. There's a term called diffusion. Diffusion is when some of the information from one letter is spread out across the ciphertext of other letters in that same message. So if I had a block of 8 characters put together and I spread the information from character 1, character 2 across characters 3 and 4, that's diffusion. And it makes it harder for the attacker to break that system. Block ciphers are good with that. They have high diffusion. Okay. Insertions have low impact. So what if I wanted to insert a new character in your stream cipher? Well, block cipher would catch that easily. Or it would corrupt the whole block. And if they change part of a block, it corrupts the whole block. So we have some error propagation problems that stream ciphers don't have as much. And we'll talk about the details of that a little later. Stream ciphers are faster because they're just doing 1 character at a time. So block ciphers are slower. Block ciphers need the padding I talked about and higher error propagation. Stream ciphers lower diffusion, susceptible to insertion. So these are some things we're going to have to worry about. When we go into actually doing these, you'll see them. So let's start with a simple transposition cipher. This is called a rail fence cipher. So imagine you have a fence with 2 rails. What you're going to do is you're going to write the letters of the message. Whoops. You're going to write the letters of the message. Where are we? Annotation. Going up and down. So I'm going to go down and then start at the top again and go down. So HELLO, WORL, D. But then when I read them off left to right. So my cipher text is this. Letters stay the same, orders all mixed up. Now, you'll notice here 2 things. I didn't include spaces when I wrote this out, but I did include a space here when I'm writing it. Typically, when we show examples of cryptography, we don't include spaces. We break things up into groups of 5 characters just to make it easier to read. Okay. In the real world, I'm using all possible letters and symbols and numbers and everything else. And so in I would have spaces, I would have commas, I would have periods, I would have upper and lower case all, and it'd be shuffled. It actually makes it a little easier to decipher. If I see how many spaces there are, then I have an idea how many words there were. If I saw 4 spaces, how many words are there? 5. Very good. Because that last word doesn't have a space after it. So we have 5 words. Okay, good. I can start playing with things. I know something about the English language. If I see a Q and a U, they probably went together. And I can start deciphering and rearranging things. The goal would be to figure out, oh, it's a rail cipher. How many rails does it have? And then once I know that, I can decipher it. Because usually that's the key to rail fence cipher is how many rails. If the message is too short, you can't have too many rails. All right. Here's one. 5 rails. This case, I did it the other direction. So that may be another part of the key. I took the cipher from left to right, wrote the plain text. So troops heading east, need more supplies, send more people now. And then we read it back top to bottom. What is that? Tidy, Rinmep, Ugus, Orieso, pay up, and never mind. So if you know the direction of the rail, you know the order, etc. Now in this case, this would be same to a rail of 1, 2, 3, I have 4, I have 10 columns, so maybe that's 10 rails. If you just transpose it, it's the same. Okay. Any questions on that? Okay, so simple transposition ciphers. Let's change it a little. Let's make the key more complex. So I know this is has 4 rows. I have 7 columns here. So, the key here Attack postponed until 2 a.m. Notice the X and the EE, that's the padding to make it fit in there. X was expected not to be in the message, so anything after X it could be just random letters for padding. So attack postponed until 2 a.m. If you wanted an X in there, maybe you put 2 X's to say, oh, that's really an X for the padding, etc. The key is the order of the columns you read. So to make this more complex, I'll read out, column 4, which is, I shouldn't have had this twice. Maybe I should have changed these to be the column numbers. Real quick, I want to change these column numbers. So columns. There we go. Okay. So column 4 is the first one. Okay, and of course I see TTNA is column 3, so I'm already off by 1. What was the next one? Column 7 started with a P. TTNA, oh, AP, so that was column 4. So it should have been, I did 3, 4, so I had the key wrong. But it gets you the idea. You pick a different column to put it out. Okay, that makes it even more complex and harder. Everybody, that one makes sense? Okay, but you're limited to number of columns. So I say, hey, I always have 7 columns. I always have 8 columns, whatever. And then I give you the key. The next part of the message would redo this again for the next 8 columns. And we would do another block if the message was longer. Okay, now, maybe we don't think that's good enough because they can see the letters that are there, the numbers that are there, and there may be key things in that really help. So let's do a substitution cipher. Let's replace one letter with another. So the Caesar cipher basically was what we call a shift cipher. It took every letter in the alphabet and shifted by 3. A shifted by 3, so B, C, D. B became, E. C became F. Oh wait, only 26 letters in alphabet. Well, we can wrap around. So X wraps X, Y, Z. Next one will go back to A. Y will go to B. Z will go to C. So the key was 3, usually written as letter D. Okay, and the ciphertext is here because H plus 3 is K. E plus 3 would get you to H, etc. Now, why would key 3 be written as a D and not a C? Zeros matter in computer science. Zeros matter in math. If you're shifting by 0, you need some letter to represent. You're shifting by 0, that's A. B is then 1, C is then 2, D is then 3. When I take my letters, I'm actually going to do them in terms of math. I'm going to take A through Z and turn them to 0 to 25. Then I'm going to add the key, so D is a 3, so 0 plus 3 would take A to a D. Would take H, let's see, H is the 8th letter, so it'd be a 7th letter, 7. 7 plus 3 is 10, which is K, yes, because J is the 10th letter, so K is the 11th, so. That makes sense? And the nice thing, when I get to 25 plus 3, that's 28, right? Mod, using modular arithmetic or remainder, divided by 26. What's the remainder? 2, 3. Actually, 25 plus 3. Oh, yeah. Right, so 26 divided by 26, remainder would be 0. So that'd be a 2. 28 mod 26 is a 2. Or 28 divided by 26, remainder 2. That would be a B, C. So the 25th, etc. All right. So in code key 3, like I said, here's the code. A is a 0, B is a 1, C is a 2, etc. up to Z. The answer is, you write it this way, the encryption algorithm is the plain text plus 3 mod 26. So 24 Y plus 3 is 27, mod 26 is a 1, that's a B. So X would get 23 plus 3 would give me a 0, 24 plus 3 would give me a 1, 25 plus 3 would give me a 2. Does this make sense to you? Doing that mod arithmetic it's remainder. We're going to keep saying mod, it's modulo. Some of you will see this in a math class eventually. I think with Math 176, they spent a lot of time on it. I'm trying to remember, my son was using it. I think it was Math 176, yeah. They do more advanced things with mod, but for me, just think of it as remainder. Okay, so decipher this. Try it. The key is not 3. How would you go? I'll even ask, how would you go about solving this?
I've
I can't hear you.
done something similar before. And what I would do is I'd go to find smaller words because they're less common. Well, I mean more common with like three letter words.
Yeah, so look at the small words. They're less common. There's some common 3-letter words that we see in our language. There's a couple 4-letter words here too. We won't worry about those. There is a double L here. Where's mine? 2 letters together. That's probably not QQ. Right? Now, in this, it's a shift cipher. That's the nice thing, because I'm telling you it's a shift cipher. So we know that if I can figure out the double L, maybe it is double L. I doubt it, but this could be L, E-L-L-E, right? If I know what those are, I solve the whole thing. If I know what this V is, I can solve the whole thing. Right? Oh, here's another double, 2 Z's, and it ends in a Z, and another Z. I'm seeing some very common letters. Hey, here's a V. What are the most common letters in the English alphabet, in the English language? A is common. E, R, O. Anybody who does Wheel of Fortune knows the common ones, right? The most common consonants, T, R, S. E is the most common letter in the English alphabet, or English language. So we can look at those and we can pull it apart. And that's what cryptanalysts do. There's actually, see if I can type this. Another thing that we use very commonly. What does it say? The book is in the library. No, it doesn't. It says the book. How did you know it says the book is in the library? The common words, there is redundancy in the English language. In any spoken language, there's extra syllables and words and letters and other things that we don't need to get the full meaning. So the book is in the library would have a lot more letters. The cryptanalyst would know that there's some redundancy. There's what we call digrams, 2 letters that go together, trigrams, common 3-letter pairs, common wording, groupings, etc. And they would say, I don't need to decipher this whole message. I only need pieces of it, and I can figure out the rest. The uncertainty of a message, what we call the entropy of the message, defines how difficult it is for the cryptanalyst to break. Here's an example. I have 4 students. One of them wins a contest. I encrypt each student's numbered. I encrypt the number. And perfect encryption scheme, how likely is it that the cryptographer can get the right person with 1 attempt? 25%, 1/4, right? 1 out of 4. What if 3 of the students were female, 1 was male, and you happen to know the winner was male? 100%. right? There was redundancy in there based on the gender of the students and some extra information. The cryptographers use that extra information, use that redundancy. They'll know things like, oh, this was a login. There's probably a prompt that says enter your name or enter the password. That's information I know is in there already, and I can help decipher it. So the cryptanalysts, the hackers, the people will try to figure this out. Anyway, I can show you the answer to this. It's on the next slide. Because I'm not going to do this right now, but unless somebody has already figured out while I was talking. What do you think ADV is? What would be a possibility? Huh? The or what?
The or the or two. That's what I think it is.
Two, TWO?
Yeah.
Okay, look at A and D. They're how many letters apart?
There's 3 letters.
It's not gonna be T and H.
Yeah.
TWO makes sense to me. So if that's 2, now we got the key. Because we know that T here is 19, A is 0, so the key is 19. Or actually the other way, sorry. I'm doing it backwards. So I have to go take T over to A. So that's a 6, 7. That'd be a 7. Let's try this, V. So 14, what was I? O, 14 plus 7 is 21, yeah. So let's try the key of 7. So 2, that was a good call. L, what was L? L was 11, so minus 7 is 4. 2 E's, okay, that makes sense. What was the R? 17, so minus 7 is 10, that's a K. Oh, okay. D, oh, we already knew D was a W, so wait a minute, that doesn't sound right. Wook? Did I do that wrong? Oops, come on. Oh, I don't have the answer. I thought I had the answer.
And there it is.
Yeah. Weak. That's right, it was E's, not O's. Yes. Wasn't a Wookiee or half a Wookiee. So expecting 2 homework assignments this week. Oh, and there are 2 homework assignments this week, just double check. Okay, we'll stop there. Any questions?
Is the information about the modular arithmetic in the book?
Probably not. I do have a handout I will make available.
Okay, I appreciate that. I'd like to look over it more closely when I have time to think about it, beat my head against the wall.